Algebra 2. Target 22, I can write exponential growth and decay functions for appropriate situations. Day 2, we're going to look at exponential decay. Exponential growth was where your growth was based on how much you have. Exponential decay is where your decay is based on how much you have. Think of a snowball, or think of a giant piece of snow. The big snowballs, they start off decaying rather quickly because a lot of the snowball is exposed to the sun. But as the snowball gets smaller, there's less that's exposed to the sun, there's less to heat up. The smaller it gets, the slower it melts because there's less exposed to the sun. That's exponential decay. Like exponential growth, you're multiplying by a certain amount every time. Same thing with exponential decay. You're going to multiply by a certain amount every time. All right. Another example is we got carbon dating. Animals and plants absorb carbon throughout their life. They absorb carbon to keep it at a steady rate. Right? Once an animal or a plant dies, the carbon intake stops, and it's got a set amount of carbon. And then over time, the amount of carbon left in that body decays at a certain rate. And you've heard of carbon dating. That's what they use to tell how old fossils and artifacts are. So you can see that here in this example, half of the amount is left after, it looks like 5,000 years. Another 5,000 years, half from there. So it goes from 100% to 50% to 25% in a matter of 10,000 years. Right? Same thing with the price of a car. Your car, the price of the car is going to go down every single year. And it's going to be based on what it was worth before. It's going to be worth a certain percent less every year. Medicine follows exponential decay. The amount of medicine in your system decreases, and your body only uses a certain percentage of what's there. In this example, a person takes a dosage of I milligrams of ibuprofen. The amount left in the person's bloodstream can be modeled by the equation A equals I times 0.71 to the T. So you can see after 1 hour, they have 71% of what they started with. Think about what that means as far as how much they lost. After 2 hours, they have approximately 50% because they lost 71% of what they had before. And it continues. Every hour they keep 71% of what they had the hour before. The exponential decay model is a lot like the exponential growth model, except instead of adding a rate, you're subtracting a rate. And that should make sense because you want to go down, you subtract a percentage. All right? So when a real life quantity decreases by a fixed percent every year or any other time period, the quantity after t years can be modeled by the equation y equals a times 1 minus r to the t. A is the initial amount, r is the percent decrease. So if you think back, if you kept 71%, you lost 29%. So there's a 29% decrease in that last example. And 1 minus r is a decay factor, meaning you were keeping 71% of what you had. All right, so example, a new snowmobile costs $4,200. The value of the snowmobile decreases by 10% each year. Write an exponential decay model giving the snowmobile value after t years. Estimate the value after 3. Graph the model and use the graph or equation to estimate when the value of the snowmobile will be $2,500. So the first one, write an equation. Vy equals a times 1 minus r to the t. We're decreasing by 10%, so that's our value. 10% is 0.1. Move the decimal point twice. 0.1. So y equals our initial value of 4,200 times 1 minus 0.1. If you lose 10%, you keep 90% to the t. So there's our equation. Estimate the value after 3 years. We're going to stick 3 into our equation. So we got 4,200 times 0.9 for 3 years. So after 3 years, that snowmobile should be worth about $3,061.80. If we're going to graph that, we'd graph our equation with T. $4,200 times 1 minus 0.1, or 0.9, to the x. Think about our window. T is represented by x. Probably want to start your minimum value of T at 0, because that's when you buy the snowmobile. Probably keep this snowmobile, let's say 5 or 6 years. Let's take the scale of 1. Minimum value of the snowmobile, I hope it doesn't go any lower than 0, so we'll keep 0. And the maximum value is 4,200. That's what you bought it for. And let's make our scale in this one, let's try 500. And then as we graph it, you can see there's the cost of the snowmobile over time. You can see how it's going down. It's going down at a steeper rate, but then as it gets older, it's going to go down at a slower rate because there's less value to begin with. They can't lose as much. All right, and our last question, use the graph to estimate when the snowmobile will worth $2,500. Let's graph the 2,500 in Y2. Just see when they cross. And you can see that they cross right here, which appears to be pretty close to the 5th year. So after year 5, the snowmobile will be worth about $2,500. Be a little bit more exact if you want. If you know how to use a calculator, you can do a second trace and find the intersection of those two graphs. I just hit enter 3 times and it says x equals 4.9. 5 is a very accurate estimate. All right. Pause this one and give it a try. You buy a new mountain bike for $200. Value of the bike decreases by 25% each year. Write a model, give the mountain bike's value in dollars after 2 years. Use the model to estimate the value of the bike after 3 years. Well, my model would be y equals my initial value, 200. 1 minus 25%. If I'm losing 25%, I'm keeping 75% over 2 years. Doing that for 3 years, I'm going to plug 3 into that equation. $200 times 0.75 for 3 years, $84.37 is the value of that mountain bike. And so that's exponential growth and decay. Remember, they both follow the same basic form. Y equals A times 1 plus r to the t, or y equals A times 1 minus r to the t. The difference is 1 plus r, that's growth, because you're multiplying by a number bigger than 1, because you're adding 1 to it, or adding 1 to your percentage. 1 minus r, that's decay. And that'll always be a number between 0 and 1. And this will be a number larger than 1.